This section we'll talk about covariance and how that affects the variance of a portfolio. So it's titled risk over time, but it's probably not the best name. What we're thinking about here is how to build it when we're thinking about portfolios, how the relationships between the components of the portfolio affect the overall portfolio. So covariance is something that it's covered in a previous stats class, in Econ 206 or a previous stats class, wherever you took that. And this is how we calculate the sample covariance. So it's the difference between what we observe for x and the mean of x, and what we observe for y and the mean of y. So covariance is a concept that we think about when we're looking at more than one variable at a time. So if we plot two variables, x and y, if we plot something using the x and y coordinates. So let's say we have sales square footage on the x-axis and price on the vertical axis. We can think about the average square footage, that's our x bar, and the average sales price, that will be our y bar. Then x sub I and y I would be a combination of square footage and price for a particular house. So if xi is above its mean, so if x is greater than x bar and y is greater than y bar, both of these things are positive, and we would get a positive product. If they're both below their mean, so x is less than x bar, y is less than y bar, so it's a below average size home and a below average priced home, we would also get a positive because the product of two negative numbers is also positive. So we have large, expensive homes or above average size and above average price, that would be positive. If we have below average size, below average price, that would also generate positive product. So what we're really looking at with covariance is how do the variables move together? So if x is below its mean when y is below its mean, and x is above its mean when y is above its mean, we're going to get a positive covariance. But think about the opposite. Let's say we had small homes that were expensive, so x is below its mean when y is above its mean. And then we have large, cheap homes. So we have x is above its mean but y is below its mean. That's going to produce a negative covariance. So all we're really doing with covariance is measuring the relationship between x and y. Are they both above their mean at the same time, or both below their means at the same time, or is one above and one below? That's all we're doing. So if two variables are moving in the same direction, we would say that they have a positive covariance. If they're moving in opposite directions, we would say they have a negative covariance. Very basic concept. We're not going to calculate it this way in Excel. We could use the covariance formula. But the only downside to the covariance is it doesn't provide any information about the strength of the relationship. So if we're looking at covariance, positive or negative, we know if variables are moving in the same direction or opposite directions. So we believe that larger homes sell for more, so there would be a positive covariance between house size and the sales price of a house, positive covariance. But we don't know how closely those two variables are related if we just look at the covariance, because it doesn't provide any information about the strength of the relationship. So if we want strength and direction, we can use the correlation. So the correlation between x and y would be the covariance that we calculated on the previous slide. Then we divide that by the product of the standard deviations. So Sx would be the standard deviation of x, Sy would be the standard deviation of y, and that's going to give us the correlation. And the nice thing about the correlation is it's bound between negative 1 and 1. So if you think about two variables that have a perfect negative relationship, we would get a correlation of negative 1. So they're moving in opposite directions and the relationship is perfect. It's deterministic, negative 1. If we have variables that are moving in the same direction, so positive covariance, and it's deterministic, you get a correlation of 1. So if you think about, if you estimate the correlation between degrees Celsius and degrees Fahrenheit, you're going to get a correlation of 1 because they're moving in the same direction and that relationship is deterministic. So this is a rho. So this describes a perfect positive relationship when it's 1. If rho is -1, perfect negative. Rho of 0 indicates no linear relationship. So it does not mean that the variables are independent. It just means there's no linear relationship between the two variables. So if we're looking at a plot, this is no correlation. So if you look at this top left plot, there's no correlation between x and y. If you were to draw just a little grid here, find x bar, make a vertical line, find y bar, do a horizontal line. When x is above its mean, y is above or below. When x is below its mean, y is above or below. There's no real relationship between x and y, so the correlation is 0. If you look at this next plot, if we look at x relative to y, when x gets large, so does y. So these values up here on the right, x would be greater than the x bar, y would be greater than y bar. If we go down here, x is below x bar, y is below y bar, so they're moving in the same direction. So we get a correlation of 0.75. So the relationship is positive, but not perfect. If we look at the bottom left, this is a negative correlation. Notice x and y are moving in opposite directions. So this would be x is greater than its mean, but y is lower than its mean. Here, x is less than its mean, y is above its mean. So they're moving in opposite directions. Fairly right in the middle correlation of negative 0.5. And this bottom right one is interesting because we can clearly see a relationship between x and y. So in this plot, what we actually have here is y equals x squared. So this is a deterministic relationship between x and y, but the correlation is 0. And the correlation is 0 because the relationship between x and y isn't linear. Correlation and covariance are measures of linear relationships, and since this is a non-linear relationship, it's actually quadratic, we get a correlation of 0. So I put that in there just to help you understand that just because two things are uncorrelated, it does not mean they're independent. One could cause the other, and we still find 0 correlation. It's just a measure of linear association. So just be careful if someone tells you two things are uncorrelated, that does not mean they are independent, even though that may be what they mean. That's not actually true. So you have to plot it and think about that relationship between x and y. If it's linear, if it's approximately linear, then the correlation might pick it up. If it's a nonlinear relationship, correlation is not going to pick it up. So now we want to apply this to a portfolio. So if we have a portfolio of 3 stocks, A, B, and C, we need to think about how they're correlated with each other. And here's why we need to think about why they're correlated with each other. So the return simply depends on the returns of the individual stocks. So if we have WA, WB, WC, these are the weights each stock have in the portfolio. So let's say we have a 3-stock portfolio and they're equally weighted. So you have an equally weighted 3-stock portfolio. This would be 1/3, 1/3, 1/3. They have to add up to 1. If these are the returns, so the return on stock A, the return on stock B, the return on stock C, we find the return on the portfolio by multiplying the return by the weight. So let's say we have, we'll do an example in just a second. I won't try to do it on the fly. But all we're going to do is take the return on the individual stocks and then weight those by how much weight they get in the actual portfolio. So this is the weight of A times the return of A, the weight of B times the return of B, the weight of C times the return of C. This is where we have to think about the relationships among the variables. So return is easy. It's just a weighted average of the individual returns. But for the variance of a portfolio, it's a lot more complicated, and we're going to see, let me actually back up one second here. So notice right here we have the correlation is rho xy times rho of xy equals the covariance divided by the standard deviation. If I just want the covariance, so if I want covariance of xy, I can multiply rho xy by the standard deviations. So if I did rho xy multiplied by this will give me the covariance. So rho xy times sx sy is the covariance, and that's what we see right here. So notice the variance of a portfolio is the squared weights times the variances of the individual components. So this is the squared weight of A times the variance of A, squared weight of B times the variance of B, squared weight of C times the variance of C. This is 2 times the weight of A times the weight of B. This term right here is the covariance between A and B. So rho AB is the correlation between A and B multiplied by the standard deviation of A times the standard deviation of B. So notice we have the correlation between A and B, A and C, B and C. So the variance of the portfolio depends on all of the pairwise covariances of the components in the portfolio. So if we have 3 stocks, we have three covariances. We have A and B, A and C, B and C. So let's just say we go to 4 stocks. We're going to have A and B, A and C, A and D, B and C, B and D, and then C and D. So if we have 3 stocks, we get 3 terms right here. If we have 4 stocks, we have 1, 2, 3, 4, 5, 6 terms. So these covariance terms are going to add up pretty quickly once we start increasing the number of stocks in the portfolio. So the key to this entire set of notes, or this entire lecture, is the importance of these terms right here. So if we think about the variance of a portfolio, the variance of the portfolio is going to be higher if the variances of the individual components are higher, but also if they are positively correlated with each other, or positive covariance. So because we're adding these terms right here, if they're positively correlated, we're going to get a higher variance. If we make these terms lower, so if we subtract these covariance terms, the portfolio variance will actually get smaller. So if you build a portfolio of things that are highly positively correlated with each other, you can actually increase the risk of the portfolio. You can end up building a portfolio that has more risk than the individual components might suggest. If you build a portfolio of things that are uncorrelated, so you have industries where one goes up, the other one's going down, that can actually lower the variance of the portfolio. Because if they have negative correlations, we're going to be subtracting these terms instead of adding these terms. So these terms here are always going to be positive because all of these terms are positive. But it's what we think about these covariance terms that determines the variance of the overall portfolio. So a quick example with uncorrelated stocks here. So let's say we have 3 stocks, they all have a return of 3%, and they're uncorrelated with each other. So we're going to assume all of these terms are 0 because we're assuming all of these row terms are 0. Okay, so these are the individual standard deviations. Since the portfolio, everything in the portfolio has a return of 3%, the return on the overall portfolio is going to be 3%. So even though we're weighting WA, WB, WC, well, all the returns are the same, so we know we're going to get a 3% return. The variance, we're going to square the weights and then square the standard deviations, and we're going to get a variance of 0.000156. We don't care that much about that, but the standard deviation is what we care about, which is 1.25%. So notice the standard deviation of that portfolio is 1.25%, which is somewhere down here between stock A and stock B. Okay. So we're getting a standard deviation for the portfolio that's less than the average standard deviation of the stocks within the portfolio. Because we see that this is 1%, this is 2%, this is 3%. But even though we're equally weighting those, we get a standard deviation that's actually 0.125. It's closer down here to stock A. Let's do it again with correlated stocks. So everything's the same as before, but now we're going to assume a mutual correlation of 0.75. So we're going to go back up here, and now we're assuming all of these terms right here, all of these row AB, row AC, row BC, all of those are 0.75. So now we're going to be adding these covariance terms to our portfolio variance. So when we start adding these up, we get a bigger variance, but we also get a higher standard deviation. So the only thing that changed between those two problems is how correlated the things in the portfolio are. So when we have positively correlated components in the portfolio, again, we're assuming mutual correlation here, the overall risk increased. And that's because an increase in, if anything happens to one stock, it's going to happen to all of them in the same direction. So if one goes up, they all go up. If one goes down, they all go down, because we are assuming the returns all are positively correlated. So this is where you have to be careful when you're building a portfolio, because you don't want to build a portfolio with things that are all moving in the same direction at the same time, because doing that actually increases the risk of that portfolio. So here's a plot. So all I'm doing is I'm taking these two examples that I did right here, and I'm iterating over different values for the correlation. So if they're perfectly correlated with each other, the standard deviation is 2%, which is just right in the middle. We had a 1%, 2%, 3%. If they're perfectly correlated with each other, the standard deviation is going to be right there at 2%. Again, that's because these are equally weighted. As we lower the correlation, we actually lower the standard deviation of the portfolio. So the standard deviation gets lower and lower and lower. This is the example we had with uncorrelated stocks. If we have stocks that are negatively correlated, we actually get the standard deviation below 1%. And the reason that 1% threshold is interesting here, 1% is the least risky stock in the portfolio. So stock A has the lowest standard deviation of 1%. But what's interesting is you can build a portfolio and get a portfolio return or portfolio standard deviation that's less risky than the least risky component of the portfolio. So if your lowest standard deviation is 1%, we can build a portfolio and get a portfolio standard deviation that's less than 1% by carefully selecting stocks that have a negative correlation. So if we're thinking about the number of stocks and how that affects portfolio risk, again, here we're assuming a positive correlation of 0.4 and a standard deviation of 13%. If, again, this is assuming mutual correlation, so we're assuming they all have pairwise correlations of 0.4, and they all have a standard deviation of 13%. As we increase the number of stocks, we actually see the overall portfolio standard deviation decrease. So this 13% up here, that would be if we just have that one stock with a standard deviation of 13%, well, that one stock is your entire portfolio, so you end up with a standard deviation of 13%. As you add more and more of those, we actually see the standard deviation decrease, but then it starts to level off right here. So you can't run it to zero. So the size of the portfolio can also affect the variance of the portfolio, just like the correlation and covariance. Just like the correlation among the stocks in the portfolio can affect it as well. And that's it for this section. So the big thing here, the main thing we're taking away from this is this term right here, which is the variance of a portfolio depends on the correlation among the components in the portfolio. And if you incorrectly build a portfolio where all the correlations are positive, you're going to get even more, you can get a higher amount of risk than you were anticipating relative to uncorrelated. And this table summarizes exactly what we're seeing right there. So as the correlation decreases, so does the portfolio standard deviation, and all of that is coming through these terms right here. So you want to subtract here, you don't really want to add here. And the way we solve that is by choosing things that have some negative correlations. In the next section, we'll think about minimum variance portfolio and how we can choose these weights to minimize a variance. So the other thing we can do here is once you have the three stocks, we get to choose how much of each one we put in the portfolio. And those weights can also affect the variance of the portfolio.